Every single time you stream a movie or make a phone call or even just send a quick text, you're sending data absolutely flying down this massive information superhighway. But have you ever stopped to think about how all that traffic doesn't just crash into itself? Well, today we're going to pull back the curtain and meet the invisible traffic cops of our digital world. I mean, it sounds kind of impossible, doesn't it? How can thousands or even millions of completely different phone calls, videos, and messages all travel down one single cable at the exact same time without just turning into total gibberish? This is one of the biggest challenges, really, in all of modern communication. Well, the solution is actually pretty clever, and it all boils down to two key components. At the starting line, you've got something called a multiplexer, or MUX for short. Think of it like a highway on-ramp, merging all these different cars, our signals, into one single lane. Then, at the destination, you have its partner, the demultiplexer, or DMUX, and you guessed it, it's the off-ramp, making sure every single signal gets to its correct exit.
All right, so let's start at the beginning of this journey, right? We've got all these different signals, and they all need to merge onto that one main data highway. This is exactly where the multiplexer comes in.
So a multiplexer, or MUX, is basically what we call a many-to-one circuit. The easiest way to think about it is like a super, super fast digital switch. It takes in a bunch of different data streams, but, and this is the key, it only lets one of them pass through to the single output at any given moment. Now, the really crucial part is how it decides which one gets to go through. Okay, so how does it actually make that choice? Well, this picture here shows a really simple 4-to-1 MUX. You can see the four input lines on the left, right, labeled A0 through A3, but the real magic, the secret sauce, is down at the bottom. Those are the selection lines, S0 and S1. These two little lines are everything. They're the ones that tell the MUX exactly which of the four inputs gets the green light. And this chart here, in electronics, we call this a truth table. It lays out the super simple logic behind it all. See, the selection lines, S1 and S0, they use binary code. That's just a language of zeros and ones. And that code acts like a digital address. So if the lines are set to 0 and 0, the MUX picks input A0. If they're 0 and 1, it picks A1. You see the pattern. It's just a really straightforward, perfect system for grabbing exactly one input from the whole group. Okay, so let's do a quick check to make sure you're with me. Looking back at that truth table we just saw, if the select lines are set to, let's say, 0 and 1, which input do you think gets picked? Yep, you got it. It's input A1. And see, by changing that binary code on the select lines incredibly fast, the MUX can just cycle through all the inputs, A0, A1, A2, A3, over and over again. It takes a tiny little slice from each one and sends it down the line. That's how you get multiple conversations to share just one channel. All right, so our data made it onto the highway. Now let's jump to the other end. The combined signal has arrived at its destination, but it's still all jumbled together. It needs to be sorted back out. And that, my friends, is the job of the demultiplexer. The demultiplexer, or DMUX, does the exact opposite of the MUX. It's a one-to-many circuit. It takes that single combined stream of data that's coming off the highway, and it acts like a mail sorter, or a data distributor, routing every piece of information to the one correct output line. And what's really cool is that the whole mechanism is perfectly symmetrical. Just like its partner, the DMUX, uses those same select lines to figure out where to send the data. So if the MUX used the code 01 to send the signal from input A1, the DMUX on the other end sees that exact same 01 code and knows, this piece of data needs to go to output Y1. It's a perfect match.
This chart really sums it all up nicely. The MUX, that's a data selector. It takes many inputs and funnels them down to one output. The DMUX, that's a data distributor. It takes that one input and sends it out to one of many outputs. One merges, the other separates. They're literally two sides of the same coin, and they have to work together perfectly to keep our data flowing.
Okay, a 4-lane on-ramp is great and all, but our world runs on billions of signals, right? So how on earth do you scale this up? Well, this is where the design gets truly brilliant. It's all about modularity. See, you don't have to start from scratch. It's kind of like building with Legos. You just connect the smaller pieces to make something bigger. This diagram shows exactly how you can build a larger 8-to-1 MUX by just using two of those smaller 4-to-1 MUXes we just saw. So each 4-to-1 handles 4 inputs. Then their outputs become the inputs for another final MUX that makes the last choice. And all you need is one extra selection line, S2 in this case, to decide which of the first two muxes even gets to play at that moment.
And honestly, this is a huge fundamental idea in all of digital electronics. You can build these unbelievably complex systems just by combining really simple standard building blocks. By just chaining these muxes together, engineers can create systems that can handle a truly massive number of signals.
So, we've gone through the theory, which is cool, but where do these little digital traffic cops actually live in the real world? What's the big takeaway? The answer is, they're pretty much everywhere, silently running in the background and making our digital lives work.
I mean it. Every time you connect to the internet, they're there. They are the backbone of computer networks, making trillions, literally trillions, of these little routing decisions every second all over the world. They're inside your computer, helping the processor grab the right piece of data from memory. They're even in your TV, helping it figure out if you want to watch your cable box or your game console.
You know, this quote from the source material really just nails it. They aren't just handy or useful. They are essential components. Without the simple, elegant logic of the mux and demux, our high-speed, totally connected world, well, it just wouldn't work the way it does, at all. When you really think about it, this whole thing boils down to a simple switch that can only pick one path at a time. That's it. And from that one simple rule, by combining millions of them, we've built a global communication network. It kind of makes you wonder, right? What other incredibly simple rules are out there, silently running the complex digital world we rely on every single day?